Thank you for inviting me to talk about computational storage and the associated design challenges in the context of Eusocial storage. I'm Nidish Kamath, part of Kioxia strategic marketing team, and will be presenting today's talk from the perspective of an SSD vendor. Many of these aspects are also applicable for other storage devices such as hard drives or larger storage systems. The storage industry standards body, SNIA, defines computational storage as systems or architectures that provide services related to offloading the processing of or reducing data movement to or from storage. What are the factors that drive the adoption of computational storage? First, the I/O bandwidth in a system is an expensive resource due to the limited PCIe lanes on CPUs and storage devices. Second, architectures are migrating from a one CPU fits all approach to finding the best fit processor for a given task. For example, CPUs are closest to fast DRAM in the system. SmartNICs control the point of data egress or ingress in a system, and storage devices store data on which transformations are performed. In this example, depending on the type of applications, the CPU or the SmartNIC or the SSD may each be the best candidate for performing a computing task. The next factor is the rise of edge computing. Edge devices, many of which are systems whose main purpose is to collect and store data, come with inherently small limits on power budget, mechanical size, or energy efficiency. Some examples of these systems are cameras or environmental sensors. In today's data-centric view of computing, these limitations of bringing the ever-increasing data set sizes to the CPU for processing push the storage architects and the system architects to look at scale-out architectures. By extension, this search for scaling out the architecture also means a search for uh, opportunities of computational offload. Finally, there are physical limitations as to how fast the data can travel from the storage device to CPU cores. And this gap can only be solved by innovating in the physics of storage media or reducing the overhead of accessing the storage. I will be walking you through some of the exciting industry activities related to the last two items shown in the list. Let's first look at the system bottlenecks. The fifth version of DDR specification is now publicly announced by JEDEC and is expected to start appearing in the next generation of CPUs as early as next year. Similarly, the version 5.0 of PCIe, publicly released as of 2019, is also expected to show up in products within the next couple of years. What do all these changes or migration of the standards mean for data analysis and data storage? What both these standards do is increase the aggregate throughput of systems. DDR5, by increasing the aggregate bandwidth between the CPU and memory, and the PCIe 5.0 standard by doubling the bandwidth from CPU to storage devices. Storage devices are also getting help on another constraining factor, namely power. The familiar 2.5-inch drive also known as U.2, uh, is power limited to 25 watts today. These devices will eventually be phased out and will be replaced by those which conform to the EDSFF standard that allows up to 70 watts of power consumption. Every non-volatile medium, whether it is flash or other technologies such as PCM, ReRAM, or MRAM, needs a predetermined amount of energy per bit for write traffic. Hence, some portion of this increased power budget, the 70 watts, will appear as increased write performance on these storage devices. But the 70 watt limit is high enough that there will be enough power left to perform computing tasks in storage devices of the future. Next, we look at another industry dynamic, one attempting to reduce the overhead delay tacked on to transactions that access storage. Compute Express Link, also known as CXL. It's a transport layer spec that will be supported by CPUs starting with the PCIe version 5.0. It's cache coherent and brings memory-like access transactions to PCIe. Prior to CXL, the most effective way to use PCIe attached storage devices was by accessing them as block storage. In such a mode, the operating system initiates a DMA of stored data from the SSD to the pre-allocated regions in the CPU attached DRAM called page buffers. Applications would then subsequently access this paged data from the DRAM buffer. CXL allows CPUs and devices to interact as if they are peers. This peer relationship is with respect to the memory map view as seen by each device. With CXL, applications can now access addressable regions in the storage device as if those regions were a cacheable extension of the main memory. This lowers the barrier of moving data from the storage to CPU cores by a factor of up to 1000. Let's look at some of the scale-out enablers of computational storage. How does the search for scale-out or the push to scale-out architectures help computational storage? So the NVMe over Fabric standard, NVMe OF, and NVMe over TCP was ratified in 2017, and it defines the encapsulation of NVMe commands in data packets of network protocols such as Ethernet and TCP. Traditionally, dedicated storage nodes would be built around a CPU and NIC or RNIC and connected to a set of storage devices within the same node. NVMe over Fabric and NVMe over TCP enables the remote storage clients to use these routable or switchable network protocols to access the disaggregated storage unit. Kioxia led the standardization of an Ethernet physical interface for the two form factors that I discussed earlier, the U.2 and EDSFF. As part of this ratified standard, NVMe over Fabric encapsulation and decapsulation can now be offloaded to the SSD. So system integrators can use this offloaded ability to simplify the storage node architecture. What used to require a CPU or RNIC, or at the very least a smart NIC, is now implementable using a transparent Ethernet traffic aggregator chip and the Ethernet SSDs as shown in the diagram. As an added benefit, the overhead of accessing scale-out storage is now significantly reduced in this implementation. Now we come to the most recent and exciting development in the storage world. The SNIA Computational Storage Twig, or Technical Working Group, as it's shortly referred to as, is working on defining the APIs for computational storage systems. Furthermore, some aspects of these APIs are being carried forward into defining extensions for NVMe command sets, extensions that would allow a host CPU to request storage devices to perform compute tasks on the stored data and subsequently retrieve the results or status. These extensions allow efficient control flow for offloading compute tasks to storage devices and also utilize storage device bandwidth efficiently. Data transformation pipes can also couple these compute extensions with the NVMe over Fabric endcaps discussed in the previous slide to perform offload on storage devices that are spread out across a network without being limited to the confines of a single server node. How can we leverage these developments in cross projects and research areas such as Eusocial storage and Skyhook? Gartner, which updates and publishes its qualitative view of various emerging technologies as a hype cycle curve, recently called out computational storage in its July 2020 release of the curve. As seen here, it is still early in the acceptance phase, with a lot of excitement in the technical community, but with overblown expectations among early adopting customers. This provides a rich opportunity for identifying research problems and solving them collaboratively. The first area of research that I can suggest is discovery or the orchestration mechanisms, where the orchestrating entity in a Eusocial storage system queries the various capabilities of devices, formulates a latency and performance view of the cluster, similar to what routers would do in a network, and then uses heuristics on this formulated table to identify best offload candidates and the chain of transformation of data. Secondly, data plane transformations can be mapped from abstract APIs or object class functions to these lower level NVMe command set extensions. For example, using the NVMe compute extensions to enhance the Skyhook DM programmable object storage functions. Such mappings would allow higher level data transformation frameworks to perform the offload in an energy or bandwidth efficient fashion. With these points, I would like to conclude my talk. Thank you all for attending this session, and I am ready to answer any questions or discuss comments that you may have about these topics. Thank you.